So this question is in front of you. PV graph is given, and you know this is isotherm graph. P proportional to 1 by V at constant temperature. Now you have to say that from these two graphs given, which is true option. Okay, T1 is more than T2, or T1 is less than T2, or they are equal, or cannot decide. Okay, now how to use this? Choose any one volume, say this mark, and at constant volume read temperatures. Okay, say here and here. This is P2, say, and this is P1. Clearly at constant volume you say that P2 is more than P1, and you know that P is proportional to VRMS square, and that VRMS square is proportional to T. That means if P2 is more than P1, that means T2 will be more than T1. That means T1 is less than T2. So this is the option. Okay, now let's move on to second law, which is, say, Charles' law. I hope you are getting this. Now for Charles' law, again at particular amount of gas, okay, and for particular amount of gas and at constant pressure. Okay, that means when P is constant, volume is proportional to T. Okay, volume is proportional to T. That means you can write V1 upon T1 equals V2 upon T2. Right? Now you write V as NR upon P into T. When you convert into a line equation, like V will be written as any constant, say M into T. And if you compare Y equal to Mx, this is the graph. M is slope. That means slope of Vt curve will be NR upon P. Say here, this is V and this is T. So Y equals to Mx. So like this, graph will be like this. Okay, it cannot touch here because you cannot reach 0 Kelvin, absolute 0 temperature. So there is dotted sign here. Now how to draw? Same thing, P and V curve for this. Now here volume is increasing, temperature is increasing, but P is constant. So P constant means P is constant, but volume increasing, so arrow this manner. Now again, what about V versus T? Oh sorry, P versus T. Again P constant and T is increasing. So again this is the curve. Now again a comparative curve. So you compare now pressure. Say this is one P1 and this is P2. Again you have to say that which is more, P1 or P2. Okay, you have to think which is more, P1 or P2. Right? Think of it. Now you know that slope of Vt curve is NR upon P. That means slope is inversely proportional to P. Now slope is again defined as theta angle. So if I say theta 1 and theta 2 for this, so tan theta is proportional to 1 by P. Now here you can say that tan theta 1 is more than tan theta 2. That means inversely proportional, P1 will be less than P2. Okay, so more the slope, lesser the pressure. So P1 is less than P2. So this was Charles' law. Let's move on to third law, Gay-Lussac's law. third law, Gay-Lussac's law. Now, for this, at constant volume, okay, and then amount of gas, same, or particular amount of gas. Now again, this will be at constant volume, pressure is proportional to temperature. Okay, that means V is constant. That means we can write P1 upon T1 equals to P2 upon T2. Now again we'll draw curve for this. So P versus T. Again, when you write P equals NR upon V into T. So again a straight line graph. So this goes like okay, like this. Any two graph will be there. So before that, this is the graph of P and T. Now, if you draw V versus T, you know that volume is constant. That means volume constant and temperature is increasing, so this arrow. Now again, graph of P and T. Sorry, VT is the one, P and V. Again, volume constant, so this curve, but pressure is increasing, so this arrow. So this is the case PV, VT and PT. Now again we'll do comparisons. So let's take this graph only. Again say this is for V2 and this is for V1. Straight line graph between P and T gives you volume. Okay. Now again you compare the slopes. We have to find again which is more, V1 or V2. So again see here, say this is theta 1 and this is theta 2. So tan theta 2 is more than tan theta 1. And you know that slope NR upon V is again inversely proportional to V. That means more theta, more slope, so lesser volume. So V2 is less than V1. Okay. So this was your Gay-Lussac's law. Fourth law is Avogadro's law, which says that at NTP, okay, 1 mole of gas has 6 into 10 to 23 molecule of gas, okay, for 1 mole. Or you can also say that equal number of moles have equal volume of gas will contain equal number of moles. Okay, and fifth, you can say Dalton's law. So let's take example, then we'll discuss about definitions. If this container contains mixture of more than 2 gases or 2 gases, and those gases should be non-reactive. Okay, non-reactive gases when taken in a container, right? Say gas 1 and gas 2, right? So total pressure you write as pressure given by gas 1 plus pressure given by gas 2. That means when 2 non-reactive gas or more than 2 non-reactive gas are taken in a container, the total pressure is the sum of all the partial pressure exerted by those gases on the container, right? So this is Dalton's law, right? Okay, let's take example. Gas 1 is oxygen and that is 1.6 gram taken. Gas 2 is, let's say N2, and say 2.8 gram is there. Volume of container, just take 0.165, okay, meter cube. You have to find P total in this case. So P total you will write partial pressure of gas 1 and gas 2. Then what you will write, N1 RT upon V, and set temperature as 300 Kelvin. Okay, so this is given for you. You have to find total pressure. So N1 RT upon V as N2 RT upon V. So this you can write RT upon V, N1 plus N2. R you will write as value of R, okay, as 25 upon 3, right, joule per mole per Kelvin. Why, see here, PV equals to nRT. Okay, so if you know some thermodynamics, you know that PV product will give you work. So joule per mole per Kelvin. Now, so here R T V is 0.165, N1 plus N2 1.6 gram and O2. So 1.6 by 32 plus 2.8 by 28, right? So this will be 100, 2500 by 0.165 into 16, 120, 1 upon 20 plus 1 by 10. So what will you do here? Take LCM and find the value of pressure. Okay, if I take this calculation here, you can find 25 into 100 upon 0.165 into 30 upon 200. Okay, so cancel it. This 15, this 0.11. So this will be 25 upon 11 into 100, 011. So 2.2 into 1000. So 2200 Newton per meter square, you can say, approximately value of pressure. So this was for Dalton's law. Let us do some graph conversions. Graph conversions means, suppose you are given V and T graph as this, okay, from A to B to C. You have to convert this graph in P and V. So now, how to convert that? See here, V and T graph is a straight line, right? So from A to B process, straight line means pressure is constant from A to B, okay? Because VT graph is straight line, so pressure constant. So say here pressure constant. Volume increasing, so volume is increasing. So from A to B, we have found this graph. From B to C, isochoric, right? Same volume, so isochoric. Now, isochoric will be again temperature is decreasing, right? At constant volume, when temperature decreases, pressure also decreases. So from B to C, this graph, right? See again, from B to C, V is constant and temperature decreasing, so pressure also decreases, right? From Gay-Lussac's law. Now, from C to A, it is having isothermal, right? Same temperature, isothermal, right? And volume is decreasing. At constant temperature, when at constant temperature, when volume decreases, so pressure increases. Boyle's law. So this will go like this. So from VT graph, you have converted to PV graph. Suppose a container is there and gas, okay, at some temperature T, initial temperature T and V, and volume V. But what is given as Vp cube is constant for that gas. That means gas is not following this equation, okay? And now you have to find temperature when volume of the gas is taken from V to 27 V. That means you have to find temperature when volume is expanded from V to 27 V, and the equation followed by gas is Vp cube equals constant. If that is given, then you can say that V1 P1 cube equals V2 P2 cube. Okay, V is given, so you need V here. P you don't know, you need only temperature, and you can convert that P into temperature as R N NR T1 upon V1, right? And V2 NR T2 upon V2 whole cube. You can see here NR you can cancel, okay? So remaining you will have is T1 cube upon V1 square equals T2 cube upon V2 square, and you need final temperature, okay, because initial is T. So this equation, when you look here, T2 cube will be T1 cube V2 square upon V1 square. That means T cube, because T1 is T, V2 is 27. So 27 V upon V whole cube. This you can write, square. This you can write 3 cube and then square. This is T2 whole cube. So finally T2 you will get 9T. So this is also a case when any law is given for you, okay? One concept is on the basis of conservation of moles. Let's check with the example how to do that. If I take 2 containers maintained at P naught V naught and P naught V naught. Temperature both is 300 Kelvin and 300 Kelvin. Okay. Now this was T equal to 0 condition. That means two containers were there having maintained temperature as 300 Kelvin, P naught V naught, P naught V naught, because volume of container is same and connected by a narrow tube. Narrow tube. So your pressure is equal on both sides. Now what happened? Say container 1 and container 2. Now container 1 is maintained at 400 Kelvin and C2 at the same initial temperature. Then find final pressure. Okay, you have to find the final pressure because C1 is maintained at 400 Kelvin. That means the heating is there. Okay, due to temperature increment, there will be movement, change in pressure, and change in pressure will lead to the movement of molecules or the imbalance of number of moles. Like if you say n number of moles were present, okay, in one container, you can write n as P naught V naught upon R T naught. Okay. Now because of heating, temperature is changing to 400 Kelvin. Volume will remain constant, but pressure will change. Because of pressure difference, there will be flow of moles or molecules. Now what will happen? Say after some time t, when it is heated, number of moles are n1 in first container and n2 in second container. But you know that mole cannot escape from container, so they will have equal contribution, and n1 plus n2 will be n. Okay, right? That means there will be no flow of moles out of the container, so number of moles will be conserved, right? So when you write n1, you can say that you have to find final pressure, right? And final pressure also will be a common pressure. So say P is the common pressure. So P V naught upon R. Now T is changing to 400 Kelvin for N1. Okay, plus P V naught upon R 300, because container 2 is maintained at same initial temperature. Now N will be total N of C1 and C2. So 2 into P naught V naught upon initial R into 300. This will be twice N, because for one container this is N, so this will be twice N. Okay, so 2 into P naught V naught upon R 300. Now you can cancel some common terms. So you are left with P by 100, if you say 1 by 4 plus 1 by 3 equals 2 P naught upon 3 into 100. So again, to cancel our common terms, you will be left with P and then take LCM 12, 3 plus 4 here, 2 upon 3 P naught. Again you cancel this common terms. Now from here you can get P. You have to find P, so P will be 8 upon 7 P naught. So this is the final pressure, 8 upon 7 P naught, and here we used conservation of moles. Okay, so in next session we will start from the basic introduction of thermodynamics. We'll see what is degree of freedom, CP, CV, all those things from the next chapter, and we'll start with some few problems regarding this chapter. So keep on revising. Thank you.